In our last video, we left off by decomposing the first of two partial fractions necessary to take the inverse Laplace transform. And we did the easier one first, the one with 1 over s squared s plus 2, and this is what it decomposed into. And now what we have to do is we have to decompose the second fraction. This time it contains the e to the minus s. And all we're going to do is we're just going to ignore that e to the minus s. So let's just say that we have 1 plus s over s squared s plus 2, or 2 plus s, and we're going to decompose that. So that's going to be a over s plus b over s squared plus c over s plus 2. And now what we can do is we can just go ahead and solve for our a, b, and c. And at the end, what we'll do is we'll just put that e to the minus s back in. So it's going to become s plus 1 equals as s plus 2 plus b s plus 2 plus c s squared by multiplying through by the common denominator. And then if we were to distribute, we would get s plus 1 is going to be equal to as squared plus 2as plus bs plus 2b plus cs squared. And of course, we can't forget that there's a 0s square in here. So that way, when we go to create our system, we know what to do with that s squared. And so here's our system. It's a pretty easy one. We're going to have a plus c is equal to 0. Seems like a pretty familiar system. And then we look at our s terms, and we have 2a plus b is going to be equal to 1, since the coefficient of the s is 1. And then finally, we just have that 2b is going to be equal to 1 as well. And now we get a fairly easy system. Right here, we know that b is a half. We could substitute back in and then subtract a half from both sides. So we get that 2a is equal to a half, or a is going to be equal to a quarter. And we can readily see from right here that c is going to be equal to negative 1/4, since a is equal to negative c. So we're going to get that c is equal to minus 1/4. Now, we can't forget that when we do this, we have to go back and we have to make sure that we include this e to the minus s. So our inverse Laplace is going to be, we're going to have e to the minus s times 1/4 over s. And where I'm getting that from is right here. All right, so I'm just going to copy these down. Then we have bs squared. So we have e to the minus s times 1/2 over s squared. And then finally, e to the minus s minus 1/4 divided by s plus 2. All right. And of course, we could set this up for our inverse Laplace transform. All right. So we're just going to go through and break it apart, factor out the coefficients. So we're going to get 1/4 inverse Laplace of e to the minus s over s plus 1/2 inverse Laplace of e to the minus s over s squared. And then finally, minus 1/4 inverse Laplace of e to the minus s over s plus 2. All right, and so now we just find our inverses. All right, so what we're going to do is we're just going to remember that second translation theorem, where we have the unit step function. All right, so remember, the unit step function makes all of the t's become t to the, or t minus a. In this case, a is equal to 1, a is equal to 1, a is equal to 1. All right, so here's what we're going to get. We know that if the e to the minus s were to go away, this would just be 1 over s. And we know that the inverse of 1 over s is just 1. This would be 1 over s squared. So the inverse of that would be t. And then finally, the inverse of s plus 2 would be e to the minus 2t. All right. Again, that's going to be 1 over s plus 2, and that's just the normal inverse Laplace. However, because of this e to the minus s, that's going to transform everything. All right, so we're going to get, and I'm going to put this in a bracket just for this part. So we're going to get 1, right? And it's going to be 1u t minus 1 plus 1/2. Now, instead of t, it's going to be t minus 1, ut minus 1. And then finally, minus 1/4 e to the minus 2 t minus 1. And we have our unit t minus 1. Right? And that should be multiplied right here. All right. Now, another way that we could write this part of the answer is just to factor out. We could factor out a u, and I did forget the 1/4 right here, so I do apologize about that. So this will be 1/4 of the unit t minus 1. Right? And if we go all the way back up, you might remember that there's a negative right here. All right, so it is the opposite of that. We also have this animal. Okay, so what I'm going to do is I'm just going to cut this, and hopefully this will work. And so what is our answer? Right? Well, it's a juxtaposition of these animals. So I'm going to call this y at t, and that's going to be equal to, so I'm just going to take this guy, hopefully move it down. If not, then I'll just copy it. So hopefully this will come down. Nice. It's just going to come down. So it's going to be this part, right? Which was the original decomposition that we did on the first video. And we have one more part to this, and that's what we just found. So we're going to have that y at t is going to be equal to this, and then minus, now I'm going to factor out the unit of t minus 1, and that's going to leave us with 1/4 plus 1/2 t minus 1 minus 1/4 e to the minus 2 t minus 1. And of course, if we wanted to, we could do a little bit of doctoring in here where we just distribute the 1/2, combine the 1/4 and the negative 1/2. But this answer that we have is just as good as any other answer we can get. All right, so unfortunately, as you can see, being able to solve these differentials that contain the unit step function is quite tedious. Now, one other example that we can use, and this is a more real-life example, is by utilizing the forced motion system that we looked at when we started solving second-order differential equations. But let's throw in the fact of the on and off switch, or the unit step function. So we have a forced motion system. It's underdamped and contains a mass of a spring that begins at equilibrium and has a downward velocity of 1 foot per second. For the first pi seconds, we have cos equals 4t acting on the system, and then after pi seconds, the force is then halted. We know that we have a spring constant of 8 pounds per foot, and the mass is going to be 1/2 of a slug. Let's find an equation of motion. All right, so a few things we have to remember. Remember, we have this formula, my double prime, so mass times y double prime, or we can call it x double prime, because I think that's what we called it early in the course, plus beta of x prime, plus the spring constant kx is equal to some forced motion of t. So in this problem, it doesn't say anything about the instantaneous velocity. All right, so right away we can kind of get rid of this component of it. It should be obvious that f of t is going to be equal to 4t, or some derivation of that. We know that the spring constant k is 8. We know that the mass of the slug is 1/2. So this is m, and then k is equal to 8. So at this point, we have a fairly simplistic second order differential. Okay, so we're going to have 1/2 x double prime plus 8x is equal to f at t. Or another way to write that would be x double prime plus 16x equals 2f at t. All right. And of course, the question is, all right, well, what is f at t? Well, f at t is going to be a piecewise function, right? Because we have to make sure that it adheres to the fact that for the first pi seconds, the force is acting upon it, right? So here's our function that we probably want to use. F at t is going to be the difference, and it's going to be 2 f at t's because we have to multiply it by 2. So we know that f at t is going to be equal to the unit step function of t times cos of 4t. Right? So that should be pretty obvious, just because, well, we're going to make it go until it gets to a specific part, or it's going to go through until it from 0 until 4 pi or 4t. But then we could say we're going to subtract the unit step function from t minus pi of cos 4t. All right, now we're going to do a trick with this one, and it only works because we're dealing with time, right? We're going to get rid of this animal right here, right? And the reason being is because we know that t is greater than or equal to 0, all right? So, and so that means that we really don't, in our graph, we really don't even care about anything that happens before that. Right? So really what we're looking for is we're looking for our cosine function. And then when it starts to get to pi, all right, which is going to be somewhere down here, all right, that's where we want it to kind of flatline. All right, so right here, if that's pi, all right, since it's a -1, it should be lower. That's going to be essentially where we want to go through and say, okay, well, I've had enough. I'm going to flatline it. All right, so we can have a really nice, easy f at t. And I'm going to erase this just one more time because the function really doesn't exist in the real world before 0. Right? So we're going to have cos of 4t minus the unit step function of t minus pi cos 4t. All right. So we can go through now and we can set up our second order differential, right? So we're going to have x double prime plus 16x is going to be equal to 2 cos of 4t, right? Because remember, we had to multiply by 2 right here, minus 2 units of t minus pi times cos of 4t. All right, so that's the differential that we need to solve, right? And that's where we're going to stop this video. And we're going to finish solving it in the last video in this series. And then we're going to analyze what the solution really means.